Electricity powers our world, and we harness it through electrical engineering, the field that focuses on the application of electricity and electromagnetism in our everyday lives. Just as you have blood pumping through your veins, machines and systems often need electrical power flowing through their wires to work. It's the lifeblood of our society, and it's hard to imagine society today without three of the main branches of electrical engineering: telecommunications, power and lighting, and computer engineering. They each came about in their own way, with their own challenges and victories, their own heroes, and sometimes villains. And you'd be surprised how much death is involved in the history of electrical engineering. Well, it can be dangerous. Electrical engineering deals with the properties of electricity and magnetism, so it stands to reason that the field didn't really exist until we knew what those things were. No one had a very good understanding of electromagnetism until English physicist William Gilbert released his principal work, De Magnete, or On the Magnet, back in 1600. After years of experimentation, he found that the needle of a compass points north-south and dips downwards because the Earth is basically a giant magnet. He was the first to describe the phenomena we now associate with electrical attraction and magnetic poles, which is why many view him as the father of electrical studies. Now, electrical conduction, which is the movement of electrically charged particles through a transmission medium, wasn't discovered until around 1729 by a British scientist, Stephen Gray. He discovered it while doing experiments in which he connected a glass tube to various objects, like an ivory ball or a piece of cork, by wire or string. When he rubbed the glass tube, creating friction, he found the object at the other end of the line would be electrified. With the age of discovery and colonization upon the world, could Gray's work be used to produce a faster means of communication? This brings us to the start of the first field of electrical engineering: telecommunication. Efforts to communicate over long distances by things like semaphore were undertaken as early as the 1700s, but it wasn't until 1837 that Sir William Fothergill Cooke and Charles Wheatstone patented the first electric telegraph. Their design used 5 or 6 magnetic needles to sway right or left to indicate specific letters. This early model was a little impractical because of its cost, but the men later patented a new version that only used 1 magnetic needle. Their invention was clearly a neat idea, but it didn't really take off until it was used to solve a murder that sounds like it was lifted from the pages of a Sherlock Holmes novel. On New Year's Day 1845, a man named John Towle gave a woman he was seeing a fatal dose of poison. As the poison set in, she started to scream, which alerted the neighbours, and Towle ran off in a panic, thinking he escaped the law as he boarded a train from Slough to London. But his escape was foiled by technology. His description was sent by telegraph to London, where Towle was arrested and later tried and hanged. It's a rather gruesome way to make an invention popular, but it spread the story of the electric telegraph nonetheless. Around the same time as all of this was happening, Samuel Morse was making his own developments in the United States. He figured out how to use an electromagnet with a pen so that when the electromagnet was energized, the pen made a mark on paper. In 1838, he developed a system of dots and dashes, now known as Morse code, so that messages could be easily transmitted. By 1844, he had obtained financial support from Congress and built the first telegraph line in the United States. It travelled between Baltimore and Washington, and on May 24th, he sent the line's first message: "What hath God wrought?" Pretty ominous, if I do say so myself. About 20 years later, in 1866, the British ship Great Eastern succeeded in laying the first permanent telegraph line across the Atlantic Ocean. Before it, large bodies of water were a big obstacle for means of telecommunication. After the transatlantic telegraph line, some engineers began to realise that by fluctuating an electric current, they could induce different sound vibrations. It made them wonder if they could manipulate sound vibrations. Could they input a sound on one end of a telegraph line and replicate the same sound on the other end? Could they capture the human voice? By 1876, they did just that, with the invention of the telephone. A few different minds came up with similar ideas at the same time, but Alexander Graham Bell was the first to get the patent. He was able to use fluctuating current to vary the magnetism in the coil of an electromagnet, which caused a small piece of iron to vibrate on a diaphragm. This replicated the vibration that had initially sent the fluctuation, which reproduced the initial sound. Now, you could talk to people who were far away, but you still needed telephone lines and a phone with a physical connection to them. But that changed when Heinrich Friedrich Hertz discovered electromagnetic waves around 1887. It was soon realised that these waves could carry a signal by modifying their wavelength, amplitude and frequency. This led to the radio and the never-ending confusion over who gets credit for inventing it. Now, after World War I, electrical engineers manipulated these signals and found that along with the conversion of light to electrical impulses, they could create a visual broadcast. Television. Since then, we've taken these signals even further. With the internet and Wi-Fi, we've developed nearly instant wireless communication around the world. But electrical engineering is far more than telecommunication. We have electrical engineering to thank for supplying power and light. In 1801, Sir Humphrey Davy discovered that he could produce a brilliant spark, or arc, between two carbon rods in a battery circuit. This is called arc lighting. Davy's battery wasn't powerful enough to produce a stable arc, so arc lighting wasn't commercially feasible until the 1870s, after Belgian-born engineer Zenobe Théophile Gramme developed a generator that could support a higher power capacity. It was called the Gramme dynamo, a continuous current electrical generator that drove the push for electrical power. While arc lighting began showing up on streets around the world, Thomas Edison realised that arc lighting was too bright to be used in the home. This led to his development of the incandescent lamp. By capitalising on the work of many others, his incandescent lighting systems were soon featured at popular exhibits such as the Paris Lighting Exhibition in 1881 and the Crystal Palace in London. But Edison quickly gained competition, most notably from George Westinghouse and Nikola Tesla. This led to what's now remembered as the War of Currents, with Westinghouse and Tesla as proponents of an alternating or AC current against Edison's direct or DC current. Edison did his best to discredit AC currents by trying to convince the public that they were dangerous. He had animals electrocuted by AC currents on public display and even recommended electrocution as a death penalty alternative to hanging prisoners, at which he succeeded. The first person to be executed by electricity was a convicted murderer named William Kemmler, who was put to death in the electric chair in 1890. Despite his other efforts, though, Edison failed to discredit the push for AC. Westinghouse won the contract to supply electricity to the 1893 World's Fair in Chicago, and AC currents have since become dominant in the electric power industry. We also have electrical engineering to thank for many of the electronic devices we use every day. That brings us to the third field of electrical engineering: computers. In their beginning, before World War II, most computers were part of what was called radio engineering. Most of the computers' focus was on radar, radio, and early television. Their primary work was in processing the signals of those devices. Computers only began to gain a broader audience after the transistor was developed in 1947. The point contact transistor was a semiconductor device that could amplify or switch electrical signals. It allowed electrical engineers to replace vacuum tubes, which were bulky, unstable, and consumed too much power. But while the computers could be smaller, they were still pretty large. They also needed a separate integrated chip for each one of their functions. Then, in 1968, American engineer Marcian Hoff helped solve these problems. He conceived of a universal processor that could be used by all computers. His work led to the Intel 4004, the world's first commercial microprocessor. Since microprocessors were so tiny, the computers themselves could be even smaller. And that's how electrical engineers shaped the world we live in today, with telecommunications, electric power and lighting, and computers. The fact is, it takes all three of these fields, none of which even existed until a couple of hundred years ago, to work together for you to watch me right now. So today we explored the history of each of these fields, touching on such topics as magnetism, electrical conduction, telegraphy, lighting, and computers. Crash Course Engineering is produced in association with PBS Digital Studios. You can head over to their channel to check out a playlist of their amazing shows like Braincraft, Global Weirding with Katherine Hayhoe, and Hot Mess. Crash Course is a Complexly production, and this episode was filmed in the Dr. Cheryl C. Kinney studio with the help of these wonderful people, and our amazing graphics team is Thought Cafe.